Idealities and errors in communication systems, characteristics, and their solution. Welcome to our presentation. A wireless communication system transmits information from a transmitter to a receiver without there being a direct physical link between these two blocks. The channel is a representation of the air link through which radio frequency waves propagate as the information carriers from the transmitter to the receiver. Communication system theory commonly addresses the design of these information-bearing signals on the transmitter side, as well as the consideration of channel properties and the reception of these signals using filters, decoders, and error-correcting blocks. However, a lot of these theoretical considerations assume synchronization between transmitter and the receiver, which is actually one of the major challenges when implementing digital communication systems in hardware. In this project, we explore the broad topic of synchronization, which consists of several subcomponents of synchronization, and use these techniques in implementing basic communication systems.
Frame synchronization is required after a stream of bits has been detected at the receiver side to know the location of boundary between received blocks of bits. A simplified frame, including a preamble, a start frame delimiter, data, and a frame check sequence. Preamble is a sequence of known bits to let the receiver get aware of that the stream of bits contains data, not just nonsense noises. In a real Ethernet frame, it contains more parts, including the destination and source address, length of data, and padding zeros. But since we're using the radio to simulate, we can simplify our frame here. Next slide, please. Here is a simulation of frame synchronization with stereo radio. Assume time and carrier synchronization is achieved. At the transmitter side, we send the message or the data first. It's sent beyond 5G here, which has 9 bytes long. After that, we generate a CRC32 code as the frame check sequence and append after data. Then we generate the preamble sequence and append it before the payload data. The frame is made now. The blue line at the left shows the frame sent from the transmitter side. To simulate a channel, we add a Gaussian noise and remove the tag of the stream, which indicates the start point of the stream. And we got the red line on the right. At the receiver side, we use the constellation decoder to get the stream of bits back. Then we correlate the stream with the known preamble sequence to extract the payload. In this correlate access code block, thresholds can be adjusted to allow errors caused by noise in transmission. Finally, we check the CRC32 to detect any errors in payload. The 9 bytes data is recovered and shows in the red graph.
At the receiver, a signal is sampled and quantized to enable the received signal to be processed digitally to extract the encoded information. However, the sampling process is not ideal, as the transmitter clock is not synchronized with that of the receiver, and so simple clock error arises, as shown in the figure here. Timing synchronization is the use of algorithms to correct for such errors, which can be detrimental to the performance of a communication system. We focused on phase-locked loop, or PLL-based timing synchronization, due to their ease of implementation in software and good performance. A simple timing PLL, as shown in figure 1 here, adjusts the trigger for this sampling process such that an optimally sampled signal is created. Figure 2 shows the structure of an example phase-locked loop, which features a TED, or timing error detector, and a filter, which aims to minimize the error iteratively to 0. Not shown on this diagram is the interpolating resampler, which is what is used to iteratively shift the received signal in time. This is an example GNU radio flow graph showing a 16-QAM communication system in simulation. The constellation diagram below shows the received signals before timing synchronization, which is almost chaotic in nature, as shown in the figure at the bottom. After timing synchronization using the symbol sync block shown in the flow graph, the received constellation approximates very closely its ideal shape, which features 16 equally spaced points on the constellation diagram, thus allowing for accurate decoding of information and retrieve.
So in an ideal communication system, the transmitters and the receivers carriers signal oscillators will be perfectly matched in frequency and phase, thereby permitting perfect coherent demodulation of the modulated baseband signal. However, transmitters and receivers can barely share the same carrier oscillators. Communication receiver systems are usually independent of transmitting systems and contain their oscillators with frequency and phase offset and instabilities. One of the solutions to solve this problem is by using the Costas loop. After using the Costas loop, the signal became the way we want from the upper left to the lower right one. Moreover, on the right side is a picture showing the basic structure of a Costas loop. And we tested the timing and carrier synchronization signal processing blocks in an over-the-air QPSK communication system using 2 software-defined radios. As the constellation diagram on the right shows, there are 4 distinct points on the constellation diagram, which indicates accurate reception of the signal due to the synchronization blocks. And finally, here's our reference page. Thank you for watching.